Hi everyone, and thanks for joining me for tutorial 10. In this tutorial, we're going to introduce Pearson's correlation and discuss the assumptions for this. And we'll also introduce simple linear regression and learn how to interpret simple linear regression output and introduce the coefficient of determination. For the remainder of the course, we're going to be focusing primarily on the situation when both our explanatory variable and our outcome variable are quantitative or numeric. If we want to examine the linear association between two quantitative variables, we can use either Pearson's correlation, which is the parametric test, or if our assumptions for Pearson's aren't met, we can use Spearman's correlation, which is the non-parametric alternative to Pearson's. If two quantitative variables are related in some way, we can model the linear relationship with simple linear regression by using the explanatory variable to explain or predict the outcome variable. So first we'll discuss Pearson's correlation, a parametric measure of linear association between two continuous variables. Pearson's correlation ranges from -1 to +1, where values close to +1 or +1 indicate a positive association, which means that an increase in one variable is associated with an increase in the second variable. Values close to -1 indicate a negative association, meaning that an increase in one variable is associated with a decrease in the other variable. And values close to 0 indicate a weak or no linear association. The sign of the correlation indicates the direction of the association, while the absolute value indicates the strength of the relationship. With Pearson's correlation, the null hypothesis is that the Pearson's correlation coefficient equals 0. The alternative hypothesis is that the Pearson's correlation coefficient does not equal 0. P is used to indicate a population Pearson's correlation, while R is used to represent the Pearson's correlation observed in a sample. So here's the formula for calculating Pearson's correlation. You don't have to memorize this, and you'll never be asked to calculate this by hand. It's more important that you understand the concepts and how to interpret the results. But here's the formula if you're interested in how this measure is derived. With the Pearson's correlation, the methods for calculating the confidence interval and testing hypotheses are really similar to other tests that we've discussed during the course, but you use Pearson's correlation as the test statistic. This measure measures association, not causation. So we can't make any statements about a causal relationship based on a correlation coefficient. For example, if we find that exercise and life satisfaction are positively correlated, we cannot infer that exercise causes life satisfaction. It could be the other way around, or there could be underlying factors or confounders that explain why these are associated, or this association could just be due to chance. An important thing to note about Pearson's correlation is that this is only used for linear associations, but it says nothing about nonlinear relationships. So for example, let's say we're interested in the association between age and illicit drug use. This would likely show that from birth to the early to mid-20s or so, illicit drug use would probably increase, but after that, then it would begin to decline and level off at older ages. This is a real and important association, but because it's not linear, the Pearson's correlation would not work in detecting this relationship. Another thing to note about Pearson's correlation is that because it's a parametric measure, it's sensitive to outliers. So outliers may artificially increase or decrease a correlation. So as I mentioned, the absolute value of Pearson's correlation indicates the strength of the relationship. So these are approximate guidelines, but in general, anything above 0.8 to 1 would be considered very strong, 0.6 to 0.8-ish would be strong, 0.4 to 0.6 would be moderate, 0.2 to 0.4 would be weak, and 0 to 0.2-ish would be little to no relationship. So let's look at a few examples here. Here we can see a fairly strong positive correlation. This is a strong negative correlation. Here's a weak negative correlation, a very strong positive correlation, a weak positive correlation, and finally a perfect negative correlation. The assumptions for Pearson correlation are that X and Y are randomly sampled and independently obtained, X is approximately normally distributed, Y is approximately normally distributed, and finally that the joint distribution of X and Y is normally distributed. So this is known as X and Y being bivariate normal. If assumptions 3 and 4 are met, so X and Y are both individually approximately normally distributed, it's usually safe to assume that the joint distribution is normally distributed. It's important to remember that assumptions are rarely met perfectly in the real world, but they should be at least approximately met in order to estimate a correlation. So let's look at some example output from the Module 7 notes on the association between gestational age and head circumference. By looking at the scatter plot alone, we can see that there appears to be a positive correlation between these variables. So let's say we check our assumptions for Pearson's and these are met, so we estimate a Pearson's correlation in R. And we find that this is 0.78, suggesting a strong positive correlation between these variables. We can also see that the p-value associated with the correlation coefficient is less than 0.05. So we can reject the null hypothesis that the true correlation is 0 and have evidence to believe that there's a significant linear relationship between these variables. We can also state that we are 95% confident that the true population correlation for these two variables is between 0.62 to 0.88. Since this confidence interval does not include 0, we can also reject the null based on this. So let's turn to simple linear regression. Simple linear regression is used when you want to model the linear relationship between a single quantitative x variable and a single quantitative y variable. Although it can also be used to estimate the linear relationship between a qualitative explanatory and quantitative outcome variable. So we fit a line to estimate the relationship between the explanatory and outcome variable. The null hypothesis is that our beta 1, also known as the slope, of the relationship between x and y equals 0. The alternative hypothesis is that the beta 1, or slope, does not equal 0. You can calculate the confidence interval for the slope using code in R. So with simple linear regression, you're using knowledge of your explanatory variable to explain or predict your outcome variable. This is different from Pearson's correlation, where no distinction is made between x and y. So using the example of exercise and life satisfaction, a Pearson's correlation would answer the question of, are these variables associated? Whereas with simple linear regression, we would choose to denote one of these variables as x and the other as y. So say that exercise is our x variable and life satisfaction is our y variable. With simple linear regression, we're wondering if we can use knowledge of exercise to explain or predict life satisfaction. Like with Pearson's correlation, simple linear regression is used to examine the linear relationship between x and y. So using our example from earlier, we couldn't use linear regression to examine the non-linear relationship between age and illicit drug use. Essentially, with simple linear regression, we fit a line to model the linear relationship between x and y. This is the formula for the fitted regression line. The y hat is the predicted value of y for a given value of x. In other words, it is the mean y value for a given value of x. The predicted value of y for a given x is the sum of the intercept plus the slope times a given x value. So here's a visual representation of the regression line. Beta 0 is the estimate of the intercept, so the mean value of y when x equals 0, and beta 1 is the estimate of the slope, so it's the average change in y for every 1 unit increase in x. It's also important to note here that the regression line must pass through the mean point. So this is the point whose coordinates are the mean of x and the mean of y. So just to summarize, Pearson's correlation quantifies the relationship between two numeric variables and makes no distinction between x and y, whereas simple linear regression can be used to make predictions on y based on x and makes a distinction between x and y. So we use x to explain or predict y with simple linear regression. When we fit a regression line, there is nearly always some error associated with this line. The error is the difference between the observed y value and the predicted y value along the regression line. So this plot shows us our fitted regression line through our observations. Each circle shows each observed y value. The blue line is our predicted value of y for a given x. The red lines show the error or residual, the differences between the observed and predicted values. The smaller our residuals are, the better our model will be at making predictions. The variance of y given x is just the variation of observations around the regression line. It is the sum of the squared difference between each observed y value and predicted y value. The variance of y given x, or error in simple linear regression, is the same thing as the within group variation in one-way ANOVA. The standard deviation of y given x is the standard deviation of observations around the regression line. It answers the question, on average, how far do observations deviate from the regression line? So when we fit a regression line to our data, the most common method to find that line is the method of least squares, which is also known as the maximum likelihood method. This method finds the line that minimizes the variation or error around the regression line. In other words, it finds the best line that minimizes the sum of the squared difference between each observed y value and the predicted y value. This means we want to minimize the error associated with our model so that our model is better at making predictions. So if we took all the red lines shown on the previous slide, which showed the difference between each observed y value and the predicted y value, and we squared those distances and summed them all up, the best line would be the line for which that value is the smallest. So now we'll go over how to interpret simple linear regression output. The code for conducting simple linear regression in R is shown at the top, and the regression equation is shown on the top right. You can see that y for a given x equals the intercept plus the slope times a given value of x, as we've discussed. In the red box, the intercept is shown to be 103.31. This tells us that the mean value of y is 103.3 when x equals 0. The intercept can often be a meaningless statistic on its own. For example, if we're looking at the relationship between age and life satisfaction, the intercept would tell us the mean life satisfaction score for those age 0, which probably wouldn't be all that meaningful. So often, researchers will do what's known as center an x variable around its mean. This means that the mean x value will be subtracted from each x observation. For example, the mean age would be subtracted from the observed age of each individual study participant. When x is centered, the intercept tells us the mean value of y for the average level of x. For example, the mean life satisfaction score for those of the average age in the sample. Below the intercept in the red box is the slope. This tells us the average change in y for each 1 unit increase in x. For example, for each 1 unit increase in x, we see y increase by an average of 1.67 units. Just beside the intercept and the slope are the standard errors for these values. The standard error of the slope and intercept give us an idea of how close our estimates are to the true population values. We're usually most interested in the standard error of the slope. Note that the regression line represents the population's estimated mean value of y for a given x. So it's our best estimate of the true population slope for the relationship between x and y. And the standard error is telling us, on average, how far will our estimate of the slope vary from the true population slope. And plus or minus 2 times the standard error of our slope will give us the 95% confidence interval for the slope. The t-values shown to the right of the standard error measure whether or not the coefficient for the x variable is meaningful for the model. This usually isn't interpreted by itself, and you probably won't use this value, but it's used to calculate the p-value associated with your slope. The p-value tells you whether you should reject or fail to reject the null hypothesis, that the slope equals 0. Here we can see that the p-value associated with the slope is 0.003. Since it's less than our significance level of 0.05, we reject the null hypothesis that the slope equals 0 and conclude that we have evidence to believe that the slope is not equal to 0. The residuals are shown at the top and represent the difference between the actual or observed values for the outcome variable and the predicted values from your regression model. So this is the error that we talked about earlier, how much individual observations of y move from the regression line. You can plot the residuals as a way to check the assumptions, which we'll discuss in the next tutorial. The residual standard error is the standard deviation of your residuals. It tells us how far individual observations move from the regression line on average. The R-squared is a metric for evaluating the goodness of fit for your model. It corresponds to the proportion of the variability in y that is explained by x. The values of the R-squared range from 0 to 1. The closer the R-squared is to 1, the better our model is at making predictions. This is calculated as the variability in y values that is explained by x divided by the total amount of variation in the y values. The F statistic tests the null hypothesis that all of the betas for the covariates or explanatory variables are equal to 0. In this example, we only have one covariate or explanatory variable. Since our p-value is less than 0.05, we reject the null hypothesis and conclude that we have evidence to believe that the covariate x has predictive power in our linear model. So let's try some example problems. UBC students were randomly and independently sampled, with the data shown below, to answer the question of whether distance from campus in miles is associated with GPA. Conduct a hypothesis test at the 0.05 significance level. So the question is if two quantitative variables are associated. It doesn't ask if distance from campus predicts or explains GPA, only if they're associated. So we can test this by calculating a Pearson's correlation, if the necessary assumptions are met. The null hypothesis is that the Pearson's correlation coefficient equals 0, and the alternative hypothesis is that the Pearson's correlation coefficient does not equal 0. We know that participants are randomly and independently obtained, and we can see that x and y are individually approximately normally distributed. So therefore, it's also safe to assume that the joint distribution of these variables is also approximately normally distributed. So since our assumptions are met, we calculate a Pearson's correlation test in R. And here's the output. So we can see that the observed Pearson's correlation coefficient for our sample is 0.138. This means that there is little to no positive linear relationship between distance to campus and GPA. Since the p-value associated with the correlation coefficient is 0.7, and this is greater than the significance level of 0.05, we would fail to reject the null hypothesis and conclude that we do not have enough evidence to believe there's a significant linear relationship between distance to campus and GPA. And we can also say that we are 95% confident that the true population correlation for these two variables is between negative 0.54 and positive 0.71. And so note that this does cross 0, so our conclusion to fail to reject the null hypothesis makes sense here. Here's another problem. Researchers collected data on blood hemoglobin levels, HB, and packed cell volumes, PCV, of 14 randomly and independently sampled female blood bank donors. assuming all assumptions are met, conduct a test to determine if there's a relationship between HB and PCV. So again, we have two numeric variables. Since our assumptions are met, we conduct the test and get a Pearson's correlation of 0.07. As you'll recall, a Pearson's correlation coefficient between 0 to 0.2 suggests a weak or no linear relationship. So based on this value alone, it seems like there's basically no relationship between HB and PCV. But if we look at this data in a scatter plot, we can see that there appears to be a fairly positive linear relationship. But remember, Pearson's correlation is sensitive to outliers. We can see an outlier in the bottom right corner, which is essentially artificially decreasing the positive relationship to make it seem like there is little to no relationship between HB and PCV when we estimate this correlation coefficient. So let's say you decided to remove the outlier and rerun Pearson's correlation test again. How do you think this would change your correlation? So for example, the direction and magnitude. If you conducted a hypothesis test now, would you be more or less likely to reject the null hypothesis? So the direction of the correlation would still be positive, but the correlation coefficient would be higher because you no longer have that outlier artificially pulling the relationship down. And you would be more likely to reject the null hypothesis because our correlation would be stronger or further away from 0, the null value. So here's another example. Researchers want to compare two types of diets on adolescents with similar body compositions and obesity. The data consists of measures of obesity, so with a BMI greater than or equal to 30 versus a BMI less than 30, for random and independent samples of 23 adolescents on diet A and 15 adolescents on diet B. Conduct a hypothesis test in the significance level of 0.05 and determine the size of the association. So first, which hypothesis test do we conduct, assuming the assumptions are met? We have a qualitative explanatory variable and a qualitative outcome variable, so we should do a chi-square test, assuming that the necessary assumptions are met. The null hypothesis is that the diet and obesity are independent or not associated. The alternative hypothesis is that diet and obesity are dependent or associated. We then check the assumptions. We know that participants were randomly and independently selected, and if we go back to check our observed table, we can see that all observed cell counts are at least 5. But what about the expected counts? Remember that normally, if we have a large sample size, we can usually assume that this assumption is met. But in this case, the two diet groups are pretty small, with sample sizes of 23 and 15. So it's probably a good idea to check the expected cell counts in this case. Remember that to obtain the expected cell values, we multiply the row total times the column total and divide this by the overall total. We can see that for one of our cells, 15 times 10 divided by 38 is approximately 4. So since this is less than 5, we don't meet this assumption. So because our assumptions aren't met, we can't conduct a chi-square test and must instead conduct the Fisher's exact test, which is the non-parametric alternative. So we conduct a Fisher's exact test in R using the code shown at the top of the slide, and this gives us a p-value of 0.15. Since our p-value is greater than 0.05, we fail to reject the null hypothesis and conclude that we do not have enough evidence to believe that type of diet is associated with obesity. In the next tutorial, we'll go over simple linear regression assumptions and how to check these. We'll expand on the coefficient of determination and centering variables. We'll also introduce multiple linear regression and discuss types of models, goals of regression models, and generalized linear regression models.